Good afternoon to all. I'm Dr. Renuka Mohanraj, Associate Professor of Computer Science and the organizer of Technical Talk. Welcome to our technical talk on performance engineering and data comparison topic. I want to welcome and introduce a young, talented resource person for this afternoon session, Mr. Bimba Seresta, Associate Consultant at Innolytics, ex-Facebook engineer. So he is our Magarisi School alumni. He completed his bachelor degree in computer science from the University of North Carolina, Chapel Hill 2019. He gained experience during his bachelor study as a software engineer intern and machine learning researcher. He worked as a software engineer at Facebook for a year with the privacy and data comparison team. At present, he is working as an associate consultant at Innolytics, Des Moines, helps to write software for medical devices. He is a founder and has successfully been running his own company named Block Backup since November 2020. He's very proud to have a young founder and incredible talent with us. My heartfelt thanks and appreciation to you for accepting this event. Now it's entirely time for your presentation. Thank you so much.
Thank you, Professor Renuka, for that very generous introduction. So I'm very happy to be here. I always enjoy talking about technical topics, so I'm looking forward to giving this presentation.
Thank you so much.
Let me share my screen with everyone.
Yes.
All right. Okay, so we're going to be talking today about performance engineering. Performance engineering, some of you may have come across this industry before, some of you may have not, but it's a very, very broad topic, and we're not going to cover most of the things that are in there, and there's a lot to cover. So performance engineering can cover algorithms, data structures, efficiency. There's a whole lot, and I'm going to talk about everything through the lens of data compression, because that's the context that I know performance engineering in. But each one of these topics you could spend literally classes upon classes discussing and studying. So we'll just take one high-level picture about of what performance engineering looks like in the real world in industry settings. So hopefully this will be interesting to everybody. I find this topic really, really interesting. So before we get into it, though, let's do a quick introduction. My name is Bimba Shrestha. I'm originally from Nepal. I am, like Professor Renuka said, I am the founder of a small software company called Blob Backup. We help individuals and small businesses back up their computers to the cloud in a private, secure, and really reliable way. I'm also an engineer part-time at a company called Innolytics. And Innolytics is a consulting company that works mostly with medical device manufacturers. So think like CT scanners, X-ray scanners, MRI machines, medical images, anything that has to do with the intersection of medical imaging, devices, and technology. We operate in that space. And I will also really quickly say that we are hiring. So if you're interested in the intersection of technology and healthcare, there's some visa requirements that we have. But if you are interested, you can send me an email there and we can chat after for sure. I also worked as an engineer at Facebook a couple of years ago, back when it was still called Facebook. Now I think it's called Meta, which is an interesting name change. But back when it was called Facebook, I used to work there as a performance engineer on the data compression team. I was working on making code run faster and faster. And most of today's talk is going to be about my experience there. I did my undergrad at UNC Chapel Hill, bachelor's in computer science, and I did my high school in Maharshi School. So I know Fairfield very well. I've been in the area. I currently live in Des Moines, but Fairfield is home to me. So I'm very familiar with TM and the entire movement. Okay, so let's get to the interesting stuff. So performance engineering, what is performance engineering? To me, performance engineering, I define it as the science and art of making computer programs run fast. And I say it's a science and it's also an art because unlike other sciences, you can't follow a systematic process to achieve results every single time. There's a lot of luck involved. There's a lot of guessing. There's a lot of stumbling. you just kind of have to build up an intuition over time about how to make computer programs run fast, what makes them fast, what makes them slow. So it is as much an art as it is a science, as we'll see. But we want computer programs that run fast, very, very fast. That's our goal. So when I say performance engineering, what most of you will probably think about if you have a traditional computer science background is the concept of sorting, because in most CS course loads, the first time that a student is introduced to the idea of performance engineering and the idea that speed is an important factor when developing computer programs is when you talk about bubble sorting and insertion sorting and all the different sorting algorithms early on in your algorithms class, or your data structures class. So everyone remembers, I assume, bubble sorting. You have, you take two adjacent elements in an array, you swap them over and over in a particular way, and eventually you'll have a sorted array. And we all know from that class that bubble sorting is slower than something like merge sort or quick sort, because the algorithmic complexity of bubble sort is higher than the algorithmic complexity of those other ones. But the thing is, this is sort of an academic exercise. There are some cases in industry where people are working on making actual algorithms faster, where they're changing algorithms in clever ways to make it a little bit more efficient. But most of the time, this really does not come up that much. This is not the type of performance engineering that gets done in the industry. The type that gets done is a little bit more nuanced and subtle. This occasionally comes up. Occasionally, you'll have to tweak the actual algorithm itself, but most of the work is done not on the level of the algorithm. So we'll look into that a little bit more. So that brings up a good question. If performance isn't exactly what we think it is when we first learned it, does it even matter? Should we even spend time thinking about performance in our computer programs? Sorry, was there a question from somebody? Oh, no, okay. But yes, should we even take time to worry about performance? And everyone knows Moore's law. Moore's law says that the rate at which hardware gets better, improves, gets faster and faster. So over the years, every single year that passes, we have better chips, better microprocessors. And so it's a good question. Won't hardware just continually keep getting better and better to the point where we won't have to worry that if our algorithms are suboptimal, or if our, or if our code isn't as finely tuned as it could be? Should we really spend time worrying about that sort of stuff? That's the question. And the sad answer is that it doesn't matter most of the time. Performance simply is not the biggest priority most of the time. There are other things that you should be prioritizing over speed and over algorithmic complexity optimizing. There's other important things. There's a famous quote by a person who some of you may know, is this academic and programmer named Donald Knuth. And he has this famous quote that goes, "We should forget about small efficiencies, say about 97% of the time." Okay, premature optimization is the root of all evil. So that last part is probably, you might have seen that last part of that quote a lot more in different places. Premature optimization is the root of all evil. But the full quote, what is he saying there? He's saying that most of the time when you're spending your energy optimizing small, tiny things to make the algorithm a little faster, most of that time is wasted because there are other things that you could be doing. So if after you graduate from MUM or MIU, I'm still used to calling it MUM. After you graduate from MIU and get a job somewhere at a company, your primary role is going to be to deliver value to that company by solving some business problem by writing code. There's a lot of different ways to do it, but ultimately that's what your role is going to come down to. And performance comes up sometimes. Like sometimes it's the case that you can deliver value by making your programs run fast, but most of the time it's by fixing bugs, or by shipping a new feature, or by refactoring code. There are a whole host of other priorities that come up way, way before performance is even an issue. So most of the time, he's right. It is the root of all evil. But sometimes, on rare occasions, 97% is not 100%. Sometimes performance is everything that matters. You absolutely need speed in some cases, and in these cases there are no tricks, there's no cheat codes. You simply need to make your program faster if you want to accomplish some business task or some other task. Okay, these cases come up, and we'll look at them. So let's take a quick example. So everyone knows about the iPhone. The iPhone came out in 2008 or sometime in the late 2000s. And it was a big deal. It was revolutionary for a lot of different reasons. But one thing that it brought to the limelight, that it was still an issue before, but it became much more of a concern for developers, was the issue of battery life. And this was an issue before because, of course, people had laptops that had batteries, people that had other types of phones other than iPhones that had batteries. But because the iPhone was this sophisticated piece of mobile device that let you run all sorts of different types of software, people were using it all the time, and they noticed that certain software, certain apps made their batteries die a lot faster than certain other apps, right? And so why is that? What separates the software that kills your battery life from the software that is very easy on battery life? Well, let's look at it. So it's this idea of, is it possible to write code so that it is minimally consumptive of battery life? Is that even, does that sentence even make sense? Is that even a worthwhile endeavor? It's kind of complicated because there are a number of different things that impact battery life. Things like CPU usage, how much CPU is the software that you're writing using, how frequently, and for how long is it using that CPU? There's memory, how much memory is it taking up and letting and preventing other programs from using? Does it connect to the Wi-Fi? Is it a networked application? Do you use Bluetooth, 5G, 4G? There are a whole host of other things that matter when you're trying to figure out if your software is going to kill your device's battery life or not. And the list is long, but to be honest, there really is one thing that you should be focusing on above all the other ones. Memory matters, Wi-Fi matters, Bluetooth matters, but the biggest thing that you can do to improve the battery life of your device on your computer program is to improve its CPU utilization. This is the biggest bottleneck. This is by far and away the most important factor when it comes to draining your battery life. So if your program is running at max CPU most of the time, your battery life is going to go down really fast. If it's using a lot of memory, that hurts, but it's not the bottleneck. There are other issues that you should be concerned about first. So how do you save battery life, right? We know now that CPU is important, or CPU utilization is important, and the answer is by going fast. And I'm being kind of serious here because we computer engineers who work with chips and performance engineers really haven't figured out a way to write software that uses battery in this smart way where you're not using too much CPU, but you're also trying to sustain the battery. They haven't been able to do this sort of craft very well. What we have learned is we've learned to write computer programs that run quickly and that send the processor back into sleep mode. So the best way to make your computer programs save battery is to finish running the program and to send the processor back to sleep. Because when the processor is sleeping, you're not using a whole lot of battery. So that's if there was one trick to this whole thing, it's just to finish running the program, send it back to idle. So in technical terms, it's called race to sleep. You can look this up on Google or some academic website, and you'll get a bunch of papers that explain why it is that this is the smart thing to do when you're trying to save battery life. But here's a diagram. So it's pretty clear. When you're on idle, you're not using a whole lot of power. When you're working, you're using a ton of power. And the longer your programs keep your CPU in this spike state, the more power it's going to use and the more battery life it's going to consume. So that is the bottom line. Here's another picture or graph that sort of says the same thing. You can see the difference in wattage from idle versus not idle. So that's one area in which performance engineering really does matter. You want to, if you want to have long-lasting devices, software that is friendly to the battery, then you need to care about performance engineering. Now let's take a slightly higher level example. This is a data center, and as you can tell, it's a really, really big building. This is a data center in Tennessee. This is one of Facebook's data centers, and if you look inside one of these data centers, you'll see something that looks like this, right? It's just racks and racks full of servers and servers and servers as far as the eye can see. And this is a very complicated thing to operate. There's a lot of moving pieces in a data center. You have spinning disks, you have SSDs, you have transistors working, and there's a lot going on. You have networks, there's bandwidth that you have to worry about. But when it comes down to it, what a data center is essentially doing is converting electricity into heat. It does a whole bunch of stuff in between. That's an oversimplification, of course, but all it does is convert electricity into heat, right? And it's really, really good at that job. So this is a really, really interesting photo. This isn't quite related, but I just think this photo is really great. This is a Google data center, and you can see water vapor coming out of the top of the data center. And this looks like the data center is on fire, but that's not what's happening. This is supposed to be a good thing. When water vapor is coming out like this, it's an indication that the data center is utilizing its resources efficiently. So this is a good sign. Okay. So in a data center, like I said, it's turning electricity into heat. And the thing about electricity is that it costs money to buy from the utility companies. So a big company like Facebook has large electricity bills, and the more data centers it has, the more energy it consumes, the more power it uses, the more it'll have to pay in terms of data center costs to its utility company, right? So what we're really trying to optimize is something called compute per watt. We're trying to maximize the amount of work we can do, the amount of computation we can do, while using the least amount of power possible, right? We want to use the least amount of power, but still do a lot of work, because the less power we use, the less we have to pay in electricity costs. So I think it's really interesting how at a very small scale, like in the case with the iPhone, we're trying to maximize compute per watt in order to do something like save battery life. So performance engineering is really, really important at the small scale. And at a very large scale, like in Facebook's data centers, compute per watt, maximizing compute per watt is important there too, because you're trying to save power, which can be directly translated into money. So this is as clear a way to demonstrate business value as you can get, right? You can say, if I do this optimization or this optimization on this code, it's going to save, it's going to make the data center use this much less time to perform this set of tasks. And because it uses this much less time, it's using this much less power, and just convert that. So it ends up translating to millions and millions in savings that you wouldn't have to pay for energy costs. So it's a very, very direct way to impact data center costs. So performance engineering is important sometimes, right? It's not important all the time, but it's important sometimes. And there's this distinction I want to make before moving forward. There is what I will call efficiency, and there is what I will call performance. These are not technical terms that you'll find used in papers, but it's worth knowing this difference here. So efficiency is sort of like our sorting algorithms. It is about how much work is the program actually doing. Okay, put plainly, that's what it stands for. So when we do sorting, bubble sort and merge sort perform the same task. They take an array and they sort it. The output will be more or less the same. But bubble sort is a different algorithm. It does a lot more work, unnecessary work, than merge sort or quick sort, but they accomplish the same thing. So efficiency is really a matter of choosing an algorithm that does the least amount of work possible while still performing the required task. So it's not like you're taking the same algorithm and making it better. You're just figuring out a way to do things in a clever way so that you do less work. So that's what efficiency, that's how I'm going to be defining efficiency. And with that definition, it means that you can have programs that are maximally efficient. You can have programs that are theoretically as fast as can be. And we know this from algorithmic complexity. You can't find a sorting algorithm that is general purpose, that runs faster than the same complexity of merge sort or quick sort or any one of the log n sorts, right? You can't, it has reached the theoretical limit there. There are certain cases where you can achieve better results, but in the general case, that's true. With efficiency, you can reach that threshold. There's something maximally efficient is a term that makes sense. Performance, on the other hand, is different. Performance is sort of like doing the same work, but doing it faster. So you're taking the same algorithm and fine-tuning it so that it becomes faster and faster and faster. But it's not fundamentally, it's not theoretically a different approach, right? So let's take the example of quicksort or merge sort again. There can be two different implementations of merge sort that do the exact same thing. They sort the array and they do it in the same, using the same exact algorithm. But those two different implementations can have very, very different runtimes. They can have very, very different runtimes. One can run, in milliseconds, and one can take much, much longer than that. It can be a factor of 5 or 6 times difference depending on how you implement it. So performance is different from if. Is there a question? Oh, okay. But performance is different than efficient. Feel free to interrupt with questions. It's okay. But performance and efficiency are different because performance is about taking a certain algorithm and just making it do the work faster. So it's like forcing it to run faster than it was before. So it's taking bubble sort or merge sort and making it run really fast. So the term maximally performant doesn't make sense because you can always make an algorithm faster. It's not like with efficiency where you reach this theoretical limit. With performance, you can continually fine-tune the implementation of merge sort so that you keep getting small improvements, even if it's 0.1% or 0.1% of 1%, you can keep getting better. So let's see, my slide is taking a little second to load, so let's give it some time. There we go. So here's one other way to think about performance versus efficiency. Performance is you're trying to light up all of the transistors in your CPU when you're trying to optimize for performance. You're trying to make sure you utilize everything that's there, all of the cores, as efficiently as you can, or I should say as well as you can, so that you can perform the task as fast as possible in real time, not on some theoretical level. So that's one way that I like to think about performance. So let's take a more concrete example. So let's say we want to write some code that just goes from 0 to n and takes all the numbers from 0 to n and puts them in an array. That's the task we want to accomplish. There are a bunch of different reasons why you might want to do this. But in Python, the code might look something like this. You just loop through the whole thing, you put the elements at the end of the list result there, and then you return that list. Very, very simple. Algorithmically, efficiency-wise, this is this is a linear algorithm, and this is as fast as you can get it, right? You can tweak things to make it a different constant linear factor, but algorithmically, it is linear. That's maximally efficient, quote unquote. But if you take the same code and write it in Java, right? Same exact algorithm. The algorithm has not changed. If you look at this underlying pseudocode, same exact algorithm, same exact structure, whatever, you'll see that this is about going to be about 40 times faster than that Python code. Same exact algorithm, but completely different performance results. This makes total sense because Java is a just-in-time compiled language. Python is an interpreted language. There are a whole bunch of other reasons, dynamic allocation of lists. There's other reasons, but the point is same algorithm, same theoretical complexity, completely different performance results. So let's see. It goes to the next slide. So one other thing we could do here is, you'll notice here, when we're creating this array list in Java, we are not passing anything in as a parameter, because an array list, as you know, in Java, grows dynamically as you add elements to it, right? And in our case, we don't really want that. We can do away with that dynamic behavior. We can just say, this is how many integers are going to be in the array at the end, and it'll totally get rid of that unnecessary allocating and resizing of the array. It'll just say, okay, take this much space and hold on to it. So that seems like a very, very subtle change, but that'll give you around 4x improvements in speed if you increase n to be large enough. So again, if you look at the theoretical algorithm, same efficiency, same theoretical complexity, linear, right? But this is 4x is a big improvement. And depending on the specific thing that you're working on, it could mean, whether your project does well or whether your project doesn't do well. So that's a big improvement. Rewrite the same thing in C++ using a vector instead of an array list, same exact code, same exact algorithm. You pass in, push back the array, the element to the end, loop all the way from 0 to n. And this will be about 5 times faster. Same exact algorithm. Rewrite the same thing in C, same exact algorithm, right? It'll be about 2 times faster. So you add up all of those wins, those performance wins over from Python all the way to our C code, and you could get upwards of 1600x improvement. That's just a very rudimentary calculation. And the same, I want to re-emphasize, this is the exact same algorithm, just completely different performance results. So that was a bit of a trivial example, but I'm just trying to illustrate that efficiency and performance are quite different things. You can reach theoretical maximums with efficiency, but you cannot with performance. You can keep getting it better. You could rewrite that in assembly and go faster. You could even fine tune the C code so that it uses memory in a really smart way. You could use a smart data structure so that there's less cache misses. There's a whole bunch of different things that you could do to make that same algorithm run faster. And that's what performance engineering in an industry looks like most of the time. You're not coming up with clever algorithms. You're not coming up with completely new ways of doing things. You're taking what's existing and you're trying to find ways to tweak it so that it's a little bit faster, and those wins will add up over time. So that's kind of what it looks like. But is that not just a toy example? Like, you might think that's you surely, like, that won't be the case in a real world setting, right? So let's take a look at a slightly more realistic example. So data compression. Data compression is also a pretty large field. We'll just take a really, really narrow slice of it today, but most people know what data compression is. If you have a computer and you've ever sent a file to somebody and it doesn't, you like try to upload it on Gmail and it says, whatever threshold limit, you can't upload this, you'll try to zip it and then you'll try to send that same file. So most of us know file compression because we've done it. We just right click on a folder or a file and then we hit compress, and it'll make the size of that folder or file smaller. Pretty straightforward. You can also do that same thing from the command line. You just pass in, you just input in the proper commands and it will compress your file. We're all familiar with this workflow. The thing to note with this workflow is that there are very few computational constraints. Really, you're not concerned about the CPU usage while you're doing this compression task, because really you're compressing probably something in the megabytes, or maybe it's a gigabyte, but still, like, it's not, you're not concerned about using too much CPU. You're not concerned about using too much memory. Like, sure, it'll probably use a lot of memory, but it's not going to take that much time. It'll finish eventually, right? So there is that. And in terms of Wi-Fi and like all those other factors that we talked about when it comes to battery life, that just is not relevant in this case. So this is a very, very specific scenario for file compression. And this is not the scenario that you will see in a data center. This is not how data compression works at a large scale when data is moving around all over the place. That's a slightly different scenario. So let's look at that. So in Facebook's data centers, the way data compression works is not that manual operation where you compress a file and then you run a command to compress a file. It's much more automatic. It's much more invisible and it's transparent. It's sort of happening all the time. when data is getting sent from one node to another in the network, when data is being backed up, when data is getting sent over the HTTPS network. So it's used in a bunch of different places all the time, and it's used automatically is the main difference. It's hard to imagine a data center working well without data compression. You would need to use twice as many resources or even 3 times as many resources to accomplish the same task if you didn't have compression. So that's sort of the general idea of how it works at scale. More specifically, one area where data compression is used in a data center is when you're backing up computers. These computers could be your servers. These could be virtual machines. They could be employee computers. They could be mobile phones. But anytime you back up a computer, you're dealing with gigabytes, sometimes terabytes, sometimes petabytes of data that you need backed up in a reasonable amount of time without taking up too much CPU resources, right? There are a whole bunch of other constraints that become important. When you create a backup, say, of a server, if it's a daily backup, you don't want that backup to take longer than 24 hours because it's no longer a daily backup in that case. If it takes 24 hours to do a daily backup, then something is wrong there. And then the thing to note is there are other things happening in that server. Your backup, your data compression algorithm is not the only responsibility for that server. It's probably doing a whole bunch of other tasks that are important. So the load on the CPU has to be minimal, almost unnoticeable. It has to be close to 10% of one core in the entire server. And these servers have lots and lots of cores, like 64, 128 cores, right? So it's not like 10% of one core. You basically need to have this algorithm run so minimally that it almost is unnoticeable. All the while backing up petabytes of data. So it's a hard task to do, basically. There are also memory constraints. There are other things happening on the server that you don't want to get in the way of. So you don't want to take up too much memory either. And we already talked about time. So all 3 of those are seen in that picture. The other area where data compression comes up in a data center is with software distribution. So whenever you download a piece of software on your Mac or your PC, it will come in a packaged, compressed archive. If it's an exe file, like a setup.exe file, or if you're downloading it on a Mac, you'll get a DMG file, which you can then double click and then unpack. And when you hit install, the archive will self-extract itself onto your computer, and then it'll put the stuff in the right place, and you can run that program and then use that software, right? So a similar sort of thing happens at scale. And in Linux, some of you might know this, that the software distribution is a little bit different than in Macs and Windows. You can use RPM or APT if you're using Ubuntu, but these are software distribution mechanisms that compress your software first. And then when someone needs to install it, they decompress it. So data compression is being used. And at scale, at a data center, software constantly needs to be updated. When a new release or when a new security patch comes out, you want to get that to your data center's computers as fast as possible. And a smart distribution strategy will help you do that. And a smart distribution strategy will make use of data compression heavily. The interesting thing about software distribution that I'll point out is that this is one case where data decompression speed is actually more important than data compression speed. Usually compression speed matters, but if you're distributing software, when you're compressing the software for the first time, right, you don't really care how much time it takes because you don't just do it one time. You just compress it one time. But when you're decompressing software, when you're extracting it, installing it onto an actual computer, that's going to happen millions and millions and millions of times. The more computers you have, the more decompressions take place. So you need that to run as fast. So sometimes you have cases in data compression where there's this asymmetrical relationship where compression won't matter, but decompression matters a whole lot. For instance, with logging, it's the other way around. If you're compressing your logs, you want them to be, you want to be able to compress them and send them over as fast as possible, because otherwise it will affect how quickly you can log things. But decompression, when you're looking at it, yeah, that matters, but not as much. So you have to, decompression speed and compression speed depend on the scenario. There's also databases, right? Databases exist in data centers. That's probably the bulk of the stuff in a data center is databases like MongoDB, MySQL, Postgres, that sort of thing. And sometimes there's of course databases getting backed up, and we talked about that. You need to be able to compress the actual dump files maybe, but you can also compress the actual columns inside of your database table. In some cases, that's important. In Facebook, there were a bunch of different cases where we wanted to compress the actual column values in a specific way. And that might seem small, but when you have very, very long tables with lots and lots of data, it can really add up. So small compression's a different use case, but compression is also being used there. There's also what are called swarm interactions, and this is the last one. And this is sort of like when you make a request to a server over HTTPS, you could just go on some website. The networking infrastructure will automatically make sure that you're using.
Shankali, do you have a question?
Sorry.
No, don't worry. It's okay. So when you access a server, right, you make an HTTP request to it. The networking infrastructure will automatically make sure that you're using an encrypted channel. You don't have to say, when I say HTTPS, make sure you're using SSL. It'll just do that for you. So in the same way, you can have data compression working in the background somewhat magically like that. When packets are getting passed from one node in the network to another node in the network, data compression is in effect. It'll automatically compress stuff before it reaches the entry point of the channel, and it'll decompress it automatically on the other side. So when you're looking at it, it just looks like you're passing raw data, but data compression is working in the background. And that's probably the biggest chunk of the data compression work at a large data center, is when you're passing these bits of data around, data compression is in effect all the time. And you just don't know because it's so transparent and it's so automatic and it's invisible. So all of that is to say data compression is everywhere in a data center. And one thing I'll point out really quickly before looking at a little bit more, some more code, is because data compression is everywhere in a data center, you need to really make sure that the performance is as fast as it can be. So here, Facebook has their own data compression algorithm called ZStandard. So when you zip a file, it uses the zip compression algorithm. When you some of you may have used 7-zip. 7-zip has their own compression algorithm. So whenever you compress files, it uses their compression algorithm to compress it. Facebook has their own compression algorithm called ZStandard. And it's been fine-tuned for their use case, but it's also sometimes useful general purpose. But they have their own custom algorithm. And it's all open source. So if people are curious, they can go on GitHub/Facebook/ZSTD and find find all the code there. It's in C. It's interesting to look at. It's very, very dense and confusing, but it might be interesting for people who are interested in performance engineering. But recently, in one of their releases, they announced that they had these really, really great benchmark results for one of their releases. It's with 1.5.0 ZStandard release. For these scenarios, compression and decompression were improved by upwards of a factor of 140%. So it was 140% faster in some cases than it was before. And you'll see down there's another sentence that says it was 2 to 3 times faster than the previous release in some cases. So that might not seem all that remarkable, but again, data compression is happening everywhere in this data center, right? It's touching basically all the data that goes in there. It's being touched by this algorithm. And so 140% improvement is like crazy good. So what actually led to that improvement? It wasn't some novel algorithm. It was just a small, tiny tweak, basically. We can if we go back to our example in Java that we looked at earlier, the difference between allocating that memory ahead of time and allocating that memory dynamically using the array list made about a 4 to 5x difference in speed. That was just one line. So a very similar sort of thing is happening here. This is obviously different. To be specific, what's happening here is we're loading stuff, we're loading data into the L1 cache of the computer that's running it before that data is used. So it's a pretty common optimization trick where you pull stuff into cache that you know you'll need later, but you just take a guess. You say, we'll probably need this later, so we'll pull it in. And if we do, great. If we don't lose anything, but we'll pull it in right now in case we need it. And in the case that you do need it, you save a lot of time. So that's the optimization trick that's happening here. But notice that in both cases, in our Java case and here, it's a very, very small change. It's not a giant refactor. It's not some crazy new algorithm that was very cleverly designed. It's the exact same algorithm. The data compression algorithm hasn't changed. It's still whatever it was before. It's just this one new line has been added. And our algorithm in the Java side is still the same as the Python algorithm and the C++ algorithm. It's just we added this one line, right? That is the only difference. So performance engineering looks like this in the industry. It's not as exciting. It's not. Some people might think performance engineering is thinking about new algorithms or finding ways to come up with, tweak algorithms in a clever way. It's more this. It's more just experimenting, testing, and adding small changes that have big impacts. So this line here probably ended up giving, something like 20% improvement in that particular flow, which is remarkable. So if you do the math, right? If you do the math, if you take remember we talked about compute per watt and how much electricity costs money for these companies. And you take the average industrial electricity rate, cents per kilowatt hour in the state of California, where Facebook has most of their data centers, or Tennessee, or any one of them, you could do the math, but you really don't have to do the math to realize that it ends up becoming tens and millions of dollars in saved money that you wouldn't have to spend consuming that power, right? So it's a lot, and I'll get back to this quote again. Most of the time, 97% of the time, it won't matter. But in that small 3% of the time, it is everything. It is probably more important than a whole bunch of other things. So this. Oh, okay. Tens of millions of dollars. This can be the difference between having a company that is sustainable. It can be the difference between having that 20% improvement can be the difference between having a device, a mobile device that lasts the entire day, or having a mobile device that dies after 30 minutes, right? So it's very, very important. So I'll just say this one more time. Most of the time, you shouldn't worry about performance because there are other things. You should probably ship features. You should probably fix bugs. You should probably make the UI better. There are other ways to add value to a business or company that don't involve fine-tuning algorithms. But sometimes you need that extra little bit of speed. And in those cases, performance is really, 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 really important. So yeah, in those cases, performance is really, really important. So that's sort of it. A pretty short talk. If everyone has any questions, I'm happy to take them now. We can go back to the slides and look at them if you'd like. So yeah, any questions?
Yeah, guys can go for your question if you have, please.
I do have a question.
Mm-hmm. Yes, go ahead.
First of all, thank you for the information. It was very valuable. I wanted to ask about the startup process. Like where do you start from startup, and how do you find the funding? How do you hire people? All of these process.
Okay. You mean starting your own company?
Yes.
Okay. Yeah, so there are a lot of different ways you could do it. The way you're mentioning, so typically there will be two paths when you're starting a company. You can either what's called bootstrap a company, which is to use either your own money or money that you've taken out on a loan or money that you've gathered from friends, family, whatever, and use that as the initial seed fund. Or you can go to an actual venture capital fund or an angel investor, they call it, someone who has money whose job it is to make smart investments in other companies and then get returns, right? So depending on the type of company that you want to start, you can pick between those two. If you take the bootstrapped approach where you're using your own funds, right? If you just save up a bunch of money and try to start a company with those funds, you have a lot of advantages. You have control. You don't have to report to the person who gave you the money. You don't have to constantly get into meetings, and they'll keep asking you, like, why isn't the company growing 7% every week? Or why isn't the company doing this, this, and this? Because they have made an investment, right? When it's bootstrapped, you have a lot of control, but you also have a lot of risk, because you likely don't have as much money as an angel investor or a VC. So you have less capital to start with, but you also have that control. So it really depends on the type of company. For companies that are meant to scale really, really fast, or scale really, really fast, like, you know, a company like, I don't know, what's the recent, like Uber or Airbnb, like some crazy startup like that, then you probably want to take money from a venture capital firm, because your interests are aligned. You also want to grow fast. They also want to grow fast. So you'll probably make smart decisions. But if it's like in my case, like the backup company that I've started, it's not going to be a company that grows crazy fast. It's going to be a company that is meant to scale slowly over time. It's not the hottest. It's not like a trending area. So with that, it makes sense to bootstrap. I don't know if you have specific questions about how to make a LLC, or if you want to make a C Corp, there are things you can get into, but that's a high level answer.
Okay, yeah, that's enough. Thank you very much.
Right.
Anybody have a question, guys?
Hi, I am Sangali. I do have a little bit question. As a startup owner, what kind of benefits and what kind of behaviors you are seeking on specialists on your team? Most important things.
Sorry, say that again. I missed
As
the
a
last.
startup owner, for example, you need team, yes, and
Right.
what the most important behaviors and you will seek on our candidates.
Sure. Yeah. So with a startup, you know, hiring for a startup is a lot different than hiring for a big company. At a big company, you're typically looking for a very well-defined role. So let's say when I was working for Facebook, they were looking for a very well-defined role. They wanted someone who was a performance engineer, who knew how to write C and C++ code, who knew a little bit of assembly. And that was it. It was a very narrowly defined role. Like, if you could do this really, really well, then you're a good candidate. In a startup, it's totally different. There's no well-defined role. Whenever you join a startup, you might be programming, but you might not be. You might also be doing 5 or 6 other different things. You have to wear lots of different hats. You might be doing some marketing, some sales, some client interaction work. So for most startups, I think if it's typically just a very, very brand new startup, the most appealing thing is going to be someone who is willing to take on different roles, someone who isn't just concerned about coding, who isn't just concerned about their specific area of the industry. So someone who is able to wear many different hats and is flexible, I would say.
Yeah, thank you.
I have a question.
Sure.
To start a startup, what type of challenges you faced?
Some of the challenges, I would say that there are lots of challenges. Probably one of the bigger ones is the mental challenge. Like it is especially if you're a computer science person, right? You can make money working at any other job. There's tons of demands for software engineers and web developers. So starting your company is risky, because you might fail, and it might not make you might spend a whole year, 2 years, 3 years working on this, and you might end up losing money. Whereas if you had spent that time just doing a job as a computer science, student, you'll get tons of opportunities to work as a software. If you just worked the job, you would have for sure made a very good salary in those 3-4 years, and you would have gotten promoted. Most likely there would have been a whole bunch of other things that would have happened. So when you're thinking about that constantly, when you start a company, I know, for instance, in my case, I know that by starting a company, I'm gonna be losing money for the first little while, or I'm not going to be making as much money as I could if I continued to work at Facebook or some other company. so if keeping that in the back of your mind is hard because you know the opportunity cost is there. but there are a whole bunch of other things that are challenging too.
Thank you.
Mm-hmm.
Anybody have a question, Scott?
Yes, I have a question.
Yes.
Hi, Bimbo. I had a question regarding the performance. Like performance is dependent on a lot of factors, like both on software and hardware side.
Mm-hmm.
So how do we determine if an application has slow performance? Then what is the main bottleneck causing the issue, and what would be the better solution? Like either upscaling the hardware capacity or fine-tune the software?
So the correct answer is that it will depend. In most cases, your bottleneck for stuff like web applications and for most of the applications that people will be developing, there are probably a lot of software wins that you can have before you need to make upgrades to your hardware. Hardware changes are only required when you reach a certain level of scale. So if you're running into hardware problems, maybe it's the case that the hardware is just not fast enough and you need to scale vertically or horizontally, whatever. But before you do that, you should really take a real hard look at the code that you've written. There are probably tons and tons of small optimizations that you can do that make it run just as well on the current hardware that you have. At least that's been my experience. Certainly there are cases where it changes, but if you use a profiler, like Node.js or has a profiler, if you're working in C and C++, you can use tools like perf in Linux. You can use on a Mac or Windows, you can use their native profiler. If you're using Python, if you're writing in Python, there's lots of packages that will profile your Python code line by line, and will show you this line is what's taking up most of your CPU cycles, or it'll say this line is killing your cache. There are a whole bunch of other tools that you can use, but I would say most of the time it's a software issue. Occasionally it's a hardware issue, but at that point you're probably reaching, it's a scalability issue at that point.
Thank you. Thank you very much.
Anybody have a question, guys? If you have no questions, yes. Any have questions? If you guys have no questions, we can end up the session.
Okay, yeah, thank you everyone for coming. I always enjoy talking about this, so feel free to connect with me on LinkedIn or whatever. I'm happy to chat about various things, technically or non-technically.
Yeah, thank you so much, Bimba. It was a wonderful time with you. It's a good experience. Yeah, I hope everybody learned some new experience. Thank you so much. Bye-bye.
Thank you. Take care.
Thank
Bye.
you all. Thank you all for coming. Bye.
Thank you. Bye-bye.